So last time we started talking about how we can actually, let's say, reproduce results, how reproducible research, and how to have unbiased evaluations of algorithms. One of the problems you have when you try to apply some algorithm to some new problem is that you have to select the best settings for this algorithm, or maybe you're comparing many algorithms and you have to select the best one in some sense. And one of the problems, if you use the same data for evaluation and training the algorithm, is that you have a biased evaluation. So the standard way to avoid that is to use a holdout set to try and select the best algorithm. That basically means that you split your data in parts, you remove some part of the data and you leave it out. This is a holdout data. And then you run the algorithm on your training set with its hyperparameters. You get some output, and then you calculate the quality of this output. Now, in this particular case, we measure the quality of the output in the holdout set. It's different from the training set. Okay? So this way you get a simple procedure for finding the best algorithm or finding the best parameters for a given algorithm. But this still misses one thing, because you have learned these best parameters from specific data set, like when you learn the algorithm's parameters, the algorithm itself on the training data, now you are choosing an algorithm using some other data. So now to evaluate this algorithm selection in the end, you need to use another test set. Okay? So you use a holdout set to select the algorithm and use another test that's independent again to measure the quality of your final selection. And this is useful specifically if you use one holdout set to select parameters for one algorithm, the best possible parameter for one algorithm. And then you have another algorithm and you use the same holdout set again to find the best parameters for that. So we look at k nearest neighbors, okay? So let's say you want to choose the best k, so you find the best k value and you choose one classifier pi1 for the nearest neighbor, and then you have another classifier, let's say it's a neural network, lots of parameters to tune. You choose some specific parameter and you have the best possible neural network that you have found, but now you need to evaluate them again, so you compare them on a new set. Okay? So that's the basic idea. You have one training set for just putting through the algorithm, another holdout set for just choosing parameters for the algorithm or settings, and then the final set where you test things. Okay? Ideally, what you would like to do is to have independent sets for doing all your measurements. If you had a way of generating lots of data, you just have independent sets for everything. Okay? So you run the algorithm many times, and every time you run, you get a different result. And this way, you can measure how good your algorithm is, and in terms of how stable it is. So maybe it's good for one random selection of data, but if you have another selection of data, it's not so good anymore. So you'd like it to be stable. But the problem is you don't have a lot of data anyway, so just going through running many experiments to collect data and then measuring the performance of your algorithm for all these different data sets is not really feasible. So you'd like to have a way of making fake data sets somehow. Yeah. And this fake data set creation is what we call bootstrapping. So basically you create some data set, called the training data set, and then you create a bunch of other data sets from this original one. How do you do it? Well, let's say that you all are one piece of data, okay? And let's say your data is your age, your sex, your weight, things like that. How much money you have in the bank, things like this. And then you're my training set, and it's a representative sample of students, let's say, at the Informatics Institute. Okay? Now I would like to have some algorithm that calculates, let's say, the prevalence of heart disease depending on your age. Okay? Fine. But how good is this estimate that I get? Well, I can just calculate based on the sample. Or if I have a way of taking another sample, may have a different result. But just using one sample, how can I measure robustness? Well, the idea is that I randomly select one of you, and then randomly select one of you again. I can select the same person more than once. Okay, sampling could replace this code. And then if I do this, I don't know how many you are, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16. So if I do it 16 times, I have another 16 pieces of data that is the the same size as you, but some people might be twice or 3 times, and some people might be not in the cell. Okay. And then I can use the data to do the estimation again. And if my estimation is very different every time, that means that there's not enough data for me to make a very good conclusion. Okay? But you can also use bootstrapping in other ways. So the standard way I use it is have an algorithm, I test it on a small data set, and I see its performance. How accurate is this performance measurement? Well, you can still have, let's say, 100 examples to test it on, and for every example it's wrong or correct, let's say 60% of the time correct, 50% of the time wrong. Well, if you do a resample of the set, then you'll have a different answer, maybe 75% or 25% correct. Yeah. And I will show this in a little example soon. This is how you actually do it. You can do 3 things with the bootstrapping technique. First is how sensitive is the algorithm to the data. If I run the same algorithm, bootstrap sample of the data, how different is the result? The second is if you actually have a specific, every time you run the algorithm, you get a specific classifier, let's say. What is the distribution of classifiers that you get? Are they all very similar or are they all very different? And if you evaluate the performance of one algorithm on a small data set, then how the performance varies when you do samples of this testing data set. Okay? So this is a very simple procedure. Basically, lots of times you select a bootstrap sample from the data, and then you return this collection of data sets. And you use this in various ways. I think it's time for the example. So here. So basically you can do the same thing. If you have already cloned, then you can do the same thing, and it might be actually more helpful. So if you have installed, these are things that you might want to do yourselves. So if you have cloned, then there is one file here called Python setup. It basically has, the first line, ignore it, but the rest of the lines basically tell you what packages you need to install in your Python setup in order for you to be able to run all of the experiments and examples we have. Okay? So do you all have Python installed in such a way that you can do this command line? No? Somebody no? Yeah, you don't have Python installed. Okay. Do you run Linux or do you run another operating system?
Huh?
Which operating system do you run?
I don't understand.
Which operating system do you run?
Windows 10.
Okay. So we need somebody to help you set up Python on Windows. Okay? You probably can do that in the help desk. I don't know how to do it myself. Okay. Anybody else that doesn't have Python installed on their laptops? I mean, it's strange. I mean, I asked for having Python software on the computers of the lab, but there are no computers in the lab. So it's, anyway.
That's a way to solve the problem, isn't it?
What? Yeah.
That's a way to make sure that all the computers have Python.
Yes. I'm not sure what went wrong here. Anyway, does anybody else have Windows and Python? You do? Okay. Do you think you can help her doing? What's your name?
Harold.
Adult?
Harold.
Harold. Okay. And what's your name?
Manduba.
Manduba. Okay. Harold, can you help Manduba during the break a little bit? Okay. Thanks. Great. So if you have Python installed, then you can also go through these examples by yourselves. There are lots of minor technical things in the examples that I don't have time to explain, and I don't have super much experience with anyway. But if you go through them, then you can probably figure them out. Okay. Now, let me just say, so if you have installed Python, then you can just run Jupyter Notebook, and okay. So the first few weeks is going to be this directory where you have more stuff, and there's another directory called Python intro, and this has introductory stuff with Python and data handling, which you will go through in a couple of weeks if you need a refresher, but I will not run this now. Okay. So Jupyter Notebook Canon. So these IPy1b files are not pure Python code, they are kind of Python code embedded within some document format of some type. So you create these notebooks. So you can basically run Python code in your browser or see the output of Python code in your browser. So what we did last time was we ran through this, right? And okay, I will do cross validation later. So okay, but anyway, we said that before. There's one thing that you do: you use a holdout set to select the parameters of your algorithm. So instead of choosing just one holdout set, you can choose many holdout sets and randomly split the data between holdout sets and non-holdout sets, and it's called cross validation. Okay. So imagine that there are 3 rows of you, right? And have data for every row. And the idea of cross-validation is to say, okay, I will use the data of the first row for testing, for holdout performance evaluation, and the other 2 rows will be used for training the algorithm. And I will do this 3 times. And each time I will use one of the rows for evaluation and the rest for training. And that's called cross-validation. And we did 10 times in this scenario. And for every scenario, for every time we gave, we have a different curve for the accuracy of the algorithm as we increase the number of neighbors. Okay, the results are always different because the data that you use for training and the data you use for evaluation are different. So, but it gives you some better idea of what's the performance dependence on this K. So here we plot the average and standard error bars. So now what we can do is we can select the best possible value of the parameter K based on this cross-validation performance. And the best value that we can choose is somewhere around here, which gives also a really relatively okay value for the independent evaluation using the test set. Okay, this is what we saw last time. So bootstrapping is a slightly different idea. Okay, instead of randomly splitting the data set in K parts, we just resample from the data set many times. And every time we resample, we get a different data set, the same size as the original one. Okay, with some data being repeated. So now, what I do is I select the best possible K using cross-validation. Okay, and after I have selected the best possible K for the number of neighbors, I look at the test score. Now this is just a one number, right? So if you go back here, this is just one number, and you can see that there are very few examples in the test set, and that means that by small changes in the classifier, you have big changes in the test score, yeah, because there are very few examples. So that means that probably the test set is not big enough to have an accurate impression of the performance. Okay, it's like you have only 2 people that you in the test set. Of course, you either have 0 or 50% or 100%. If you only have 2 data points, if you have 10 data points, then it's 0, 10%, 20 to 90% to 100%. There is nothing in between, right? So obviously there is something you cannot really measure accurately, and also the less data you have, the less statistically accurate your measurement is going to be. This is another thing altogether. So how can you measure the statistical robustness of your measurement? Well, one way to do is bootstrapping that we explained. So what you do is you randomly select some examples in the test set, and then you measure the quality over this random sample. And if you do this 1,000 times, like here, you can have a histogram showing how your test score changes due to this random sampling. and this gives you an idea of how reliable your test score is. So you might have measured initially 90% accuracy, but actually if you use the bootstrap sampling idea, you can see that the accuracy could be anywhere really from 70% to 100%. Okay, it cannot really be 100% prob, but it could be somewhere there. And if you try and look at only the central, if you can remove the tails of the distribution, then you can say, oh, it's probably somewhere between 80 and 95%, but we cannot be really sure unless we get more data. Now the other way you can use bootstrapping is different. Instead of using it to randomly sample the testing data so that you get an estimate of how accurate your test score is, you can use it to resample the training data. That means that your classifier will change every time. So you have one sample of the training data, get one classifier. Take another sample of the training data, get a second classifier. And then for the same test data, you have a different score because your classifier is different. Okay? And that's a useful technique to have, because in the end, if you do this 1,000 times, you end up with 1,000 different classifiers. And this is useful because even if your classifier is one that says it's class 1 or it's class 2, then by doing this 1,000 times, you can actually have scores in between, saying, oh yeah, 900 classifiers say it's class 1, and then the 100 classifiers say it's class 2. So I'm not really sure it's class 1. Okay? So you can use this idea of bootstrapping to create a kind of very simple probabilistic model that takes into account the amount of data you have. Let's say, for example, you have only 2 data points, okay? One is class 1, one is class 2, okay? Let's say you sample 10 times. So most of the time you get one example of class 1 and one example of class 2, and some simple classifier that generates between the two. But sometimes you get just example of class 1, in which case your classifier will probably only say class 1. And sometimes you get data only of class 2. Yeah. And how often would you do that, right? So let's try and see that. Yeah. Let's try and guess that, right? So how would that work? So have one example. Let's say x1 and class 1, and then another example with x2 and class 2. Okay, so now, well, 1 times out of 4, right? You would get both examples in your data set. Am I right or am I wrong? This on-the-fly calculation is not my forte, I would say. So okay, so 1/4 of the time you get twice x1. Okay, 1/4 of the time you get twice x2, and half of the time you get x1 and x2. Okay, in your data set. So what does that mean? That means that half of your classifiers are going to be, let's say, if your x1 is here and your x2 is there in the data, then if you have a nearest neighbor classifier, basically it's going to be this thing. So why? Because if you're using Euclidean distance, then the point where these circles intersect is there, so this has to be the boundary where the classifier chooses class 1 or class 2. Okay, so here it's going to be class 1, and here it's going to be class 2. Okay, so half of the time your classifier is going to be exactly this. But the other quarter of the time is going to be always class 1 because it's only cisclad of class 1. And the other quarter of the time is going to be class 2. Okay? So that means that if you sample lots of times, then your classification probability for any point in this area, if the point is there, then it's going to say, well, I think it's 75%, I think it's the right number, class 1. And 25% class 2. Why? Why? Because, well, here it's 50% goes to class 2, which is class 1, right? So it's a probability of class 1 given, let's call this model 0. Okay, model 1. Let's call this model 2, and let's call it model 0. Okay. So So you have 3 models, and each model has a different probability, right? And this one occurs with probability 1/4, this one by 1/4, and this one by probability 1/2. Yeah. So that means that the probability of saying class 1 if your point is there, okay, let's say it's even x1, is basically the sum of these models, the probability of its model, okay, and then the probability under this model of class 1 given x1. Okay, so I have 3 models, and this basically becomes 1/4 times 1 for the first one, plus 1/4 times 0 for the second one, because the second one has only x2, and 1/2 times 1 again, because on this side you're sure that it's class 1 according to this classifier, times 1. So that's 3/4. Okay. So that's basically your first introduction to what we call marginalization, and you can think of it basically as what's the probability if you select a random classifier according to this bootstrap sample that your classifier will say class 1. Yeah. So that's the idea of this. So that's kind of the basis, the basic information about cross-validation and bootstrapping and how you can use them as general tools for evaluating classifiers or algorithms in general, for selecting parameters for classifiers and algorithms, and for estimating the sensitivity of your estimates to the data. Okay, you can do all those things with these methods, and they require very few assumptions. If your data is like a table, then you can always use this kind of algorithms. If you have more complicated data, like social network data with people that are connected to each other, then it's harder to apply these methods anymore, because things are connected. So if you remove data from one person, should you remove everybody else's data that is connected to this person in a social network? So let's say I have only you, your data of all of you, and I want to do a statistical analysis, let's say heart disease versus age or something like that. So I collect data about your health, and then I say, okay, fine, I can now do bootstrap analysis by randomly selecting a subset of you, fine. But now let's say I want to investigate your social connections. Okay? So who is more likely to be friends with whom, depending on their background and things like that. Okay, fine, you can do that. You create some kind of network. You can do some kind of network analysis, but now you cannot say I remove data of one person. What happens if you remove this data? Does the data of the other people that are connected to him get removed as well or not? Yeah. So how do you do the sampling in this setting? So you have to have some kind of model then to do this kind of free sampling, and it's not trivial. Okay. So there is no standard answer to this, which is not why I'm not going to talk about it very much. Okay. So the last thing is, of course, the gold standard for making sure your algorithms, models, or conclusions are correct is to have an independent replication. So if somebody does the same thing you did from scratch and it has the same result, then you can be sure that your result is good. Okay. And there are a couple of points that are that are important here. And the first point is that you try to replicate the study, but sometimes the study has a wrong protocol. They did a mistake. Okay? So you try and replicate, but if you want to prove that something was wrong, then you would like to change the protocol. Okay? It's also possible that they use the float analysis, like when we look at this dead salmon thing, yeah? Well, everything was fine, I mean, but then the way that they analyzed the data was wrong, so they shouldn't have gotten this result. Or the way that they interpreted this data was wrong. So then, at the end, you see the conclusion is in agreement. Okay, this is standard for independent replication. This is pretty important because there have been a few papers that say basically that up to maybe up to 80% of reported research findings are false, especially with health and things like that. At least like 60%, because of the way people are doing data analysis and of the way that they draw conclusions from the data analysis. Okay. it's hard to fix that. It's more of a cultural thing. There are not many technical problems for not doing it correctly. Anyway, I think that's okay for this thing. If you have any questions, good time to take them. Yeah.
Regarding the bootstrap, you also have a holdout set when you use the bootstrap, or
You can use the bootstrap, yeah. So the standard way for using the bootstrap and holdout is kind of like this. I did have a diagram, but I'll just do it like this. So, I'll use the paper again. Okay. So how we do it? Well, you have your original data, okay? And then what you normally do is you split in training data and holdout, okay? And then you use this to select hyperparameters. Okay. Yeah. So now this gives you some hyperparameter, let's say lambda, for your algorithm. Now the question is, where does the bootstrap come in? You can use the bootstrap as a way to create training set and holdout sets by using a bootstrap replicates of D for DT and D8. But this has the problem of that you have some data that appear both here and there. So you normally avoid that. So what you normally do is, you can say I have my data, then I get a bootstrap sample, and then you can do this again from the bootstrap sample. But again, I think this is not a good practice. So the simplest practice is basically use this to get some lambda star, your optimal algorithm or optimal parameter, and then use the original data again to get your bootstrap replicates. Okay, and then this can give you now your new classifiers, for example. Okay, using the parameters of that you have used before. So you use this holdout, either simple holdout or close validation, to have a parameter selection, and then you can use Bootstrap to see what is the actual sensitivity of your algorithm when you use the whole data, because you use the data here to select a parameter, but there's no, you don't want to throw away this data here, right? So you select a parameter, and then afterwards you select, you look at the whole data again, and you run the algorithm to the whole data, but using the selected parameter. Yeah, and that's fine then. It's also the same thing if you do cross validation, because then with cross validation you have 10 different training sets and 10 different holdout sets. So that means 10 different classifiers. So which one should you use? Well, the standard way to do it is you just use the parameter and then you use the whole training data again to get a new classifier. And then you can use the bootstrap in this context. Instead of using the whole training data just once, you use bootstrap samples of the training data. That is only useful if you really want to have the diversity of classifiers that allow you to make these probabilistic decisions about the data. If you don't care about that, then the other reason for using the bootstrap is when you have a small test set and you need to evaluate the performance of the algorithms to make sure that you can, you know how confident you should be about the result. Yeah. So a standard scenario that happens in this case is this. Let's say I have two algorithms, okay? Or let's say two classifiers that have resulted from some process like this. Pi1 and Pi2 are my two classifiers. Okay? And they give decisions based on the data, for any data I give them. And now I test them on a small test set. Now there's a problem here. How can you compare them? So if you just plot standard error bar or something like that, what happens is that one classifier will have an error bar like this, the other classifier will have an error bar like that, and you say, well, it's not significant, they look the same, more or less. Okay? But what you can do is you can use the bootstrap to do another thing. Say, you can measure how well classifier 1 did on example T, okay, minus how well classifier 2 did on example T. Okay, let's call this delta T. Okay, now you have a vector. You can have now a vector of these guys. Let's call it delta. It's delta 1, delta n. So have a vector of these deltas. And now you can use, and you have an average delta, of course. But now you can use bootstrapping to create a confidence interval over these deltas. Okay, so let's say you have 3 examples. Make it simple. Okay, you have 3 examples, and in one of them, classifier 1 is better, so you have +1. And the other one you have a 0, and the other one you have a -1. Okay, you have only 3 examples. Okay, so most of the time you have exactly these 3 examples, so the difference is 0, right? Okay, let's make 1, 0, and 0. Okay. So you say the performance of the other classifier is actually 1/3 better than the other one, right? But actually, lots of times you will end up choosing just zeros, okay? And lots of times, slightly less, you would end up choosing just ones. So you end up with a histogram like this. And I guess the zeros are more frequent than the ones, so it would be something like that. So here the performance is 0 difference, here the performance is 1/3 difference, and here the performance is 2/3 difference, and here the performance difference is 1. Okay. So you have this kind of curve of performance difference, which tells you that, yeah, the performance difference is definitely larger than 0, yeah, but not necessarily, you're not really sure exactly how it is. Okay. And this is something that you can reapply to lots of problems where, like classification, where classifiers tend to make mistakes in the same examples, right? And be correct in the same example. So the easy examples everybody makes correct, and the hard examples almost everybody guesses wrong. So you really want to measure the variability in those examples where there is some difference. And it's hard to apply a simple statistical test to do that. The simplest way is this. If you have lots of data, then actually a simple statistical test does work pretty well because of asymptotic properties. But this is basically good enough. And this also works for multiple comparisons between classifiers and stuff. Okay, so you can use bootstrapping as a practical method for doing this. Okay, and otherwise a t-test is also okay. It's not so bad. So these are basically the main methods you use. But bootstrapping itself is interesting. As I said, for creating an aggregate of many classifiers from the training data, and then using them to have probabilistic predictions. And there is a method called random forest, which creates decision trees, which is a type of classifier or regression method. And you basically resample the data lots of times, and you have very, very simple classifiers that are trained on very, very different pieces of data. And then you have thousands of those, but they're very simple. And then you can use them not just to make probabilistic predictions, but they are also much more robust than a single decision tree. Decision trees are very, very brittle methods. So yeah, this kind of technique is kind of important. And it has become, again, prominent in research, although it was forgotten for some time again. And you are free to use bootstrapping in your projects. So there's no requirement to use it. You can use anything else you like, as long as it's justified in some way. Okay, so that's it about replication, I think. So let's try and find something else to talk about. Okay, so I will start talking about decision problems. I will not finish probably, but I will start today. Okay, so think about probabilities again. I will talk a little about probabilities in this course. So we'll go through some formal things now. Now, why do we need probabilities? Well, the main reason is that we have to have a way of representing uncertainty. Okay? Think about the future. You cannot predict what's going to happen with certainty. You have some idea of what's going to happen. Okay? Will this building collapse or something? I don't know, if there's an earthquake of this magnitude, who knows? You don't know for sure what happened in the past, right? So you have some historical data, but you don't really know what happened in the past. So you have to somehow make an inference or guess about past events. Okay? So you have, it might look as though it was a different type of uncertainty, but there is a way to quantify both types of uncertainty in the same way, and that is probabilities. It's not the only way you can do it. There are many other different ways, but probabilities have one advantage. They have been used a lot. We know how to deal with them, and there's lots of computational tools that use them. So unless somebody comes up with a better way of doing it that's really better in every possible way, then people just do it this way. Okay? There are particularly some very nice logical theories, like plausibility theory, that people might like, but there are no tools at all for doing anything like that. So it remains curiosity. On the other hand, probability theory is simple. Actually, it's the basics of probability theory are very, very simple. If you know how to measure an area and of things, that's basically a probability. So I will go through the actions probability just for refresher, and I like illustrating them with some notes, let's say. So, okay, this is more. Okay, so there are some actions for probability, right? And when we say probability, we usually talk about the probability measure, okay? And there's like what we call a universe of possible outcomes, and an algebra of outcomes and stuff like that, but we don't really care so much. Think about probability as a measurement of an area of something, okay? So let's say that this is everything that can possibly happen, this thing here, it's called omega, everything that can possibly happen. And let's say this is the universe of, or the set, okay? In this set you win the lottery. Okay? So if this is a random event that happens, let's say with equal probability everywhere, or basically, let's say you randomly select a point here, and if the point is there, then you win the lottery. Yeah, that's the idea. And the larger, of course, this set is, then the more likely it is that you will win the lottery. Okay. And you can have multiple events. This one is you die of cancer, things like that. So these are all the things that can happen to you. Okay. Some things here I say that winning the lottery and dying of cancer are completely exclusive of each other. You cannot have both. Of course, probably this is not true. Maybe both can happen. So maybe A should be also extended a little bit there. Maybe there's another event here. C. Okay. So some events can happen at the same time, some cannot. And okay, let's go back here. So there are a couple of axioms here, and the first is that there's a certain event. So we know that if there's an event, it will happen in this omega, and every other event is a subset of this omega, like the circles, and the probabilities have to be between 0 and 1. That's fine. And there's one other axiom which is very simple if you think about it just as areas of stuff, right? And it just says, well, the probability of any two areas there is the same as the sum of the areas. It's normal if they are not overlapping. That's the basic of probability. There's nothing else. That's all there is to probability. So if you know that, then you're fine, more or less. Okay. So I will actually just write them down on the board. So for any event, you have this guy being 0 and 1. And for any other two events that are disjoint, which means that they cannot occur at the same time, this is just that. Okay. there is one more thing that you can infer from these rules, and this is basically that if you have, well, there's also a definition. I'll go through that. So there is one thing that is of interest to us sometimes, and this is what happens if you know that some event happened, then what's the probability of the other event? And this is very, very, very important, because if you think about one event B as somebody telling me that it's going to rain tomorrow, and A is the event that it rains tomorrow, then maybe before I actually hear this information, I have some, okay, probably it's going to rain tomorrow, and then this person tells me, no, it's not going to rain tomorrow. Maybe I believe him, and then my idea of whether it rains changes. Okay? So the definition of what is called conditional probability just says, well, the probability of one event given another event is just the probability of both of them happening divided by the probability of the second event. Okay, and then if you do it like a diagram, again, it kind of makes sense. Okay, let's go back to the diagram a bit. So let's say that you have, like here now, events A and B. Okay, so this is the area that is in common for both of them. And if you say that the probability of, let's say, A given B is the probability that you land here, given that you already have landed there. So this is really the proportion of the area of B that also belongs to A. Yeah. So in terms of areas, it also seems to make sense. Okay? But it doesn't have to be this definition, but this definition is useful because when you define conditional probabilities in this way, then the rules of probability, like this thing here especially, this addition, also holds for conditional probabilities. Okay? So if you have probability, the probability of A or B happening if some other event D has already happened, then this is already like this. It's pretty useful. Okay. And then you are basically done with probability. From these facts, you can deduce what is called Bayes' theorem, which tells you if I know the probability of one event happening, say the probability of B given A, and another probability of A and B, then you can deduce the probability of A given B from those. Okay? So I will give an example of that. And the bottom part here is basically exactly the same as this. And this is called what we already saw, the marginalization rule. So you remember we had this example where you had the bootstrap samples, and every one of these models was telling us a different probability for a class. So what we're doing, we're multiplying. So let's say B is the probability of a class. So this probability of a class given model 1, probability of model 1, probability of a class given model 2, probability of model 2, for example. Yeah. So this is exactly the same rule. It's called the marginalization rule. So you can write any probability of an event as a sum of the probability of the event given any other set of events, as long as these events are mutually exclusive. So A1 and A2 are mutually exclusive events. So the probability of B is the probability of B given A1 times the probability of A1 plus the probability of A2 given A2 times the probability of A2. And this is the basic idea of Bayesian inference. And we'll go through the examples now, or maybe after the break.